Hi, I'm David Spetzler. I'm the President and Chief Scientific Officer for Caris Life Sciences, and I'm here today to talk to you about advances in liquid biopsy. And so as we start to think about the opportunity that liquid biopsy performs and affords us, I think it's important to start to think about this in the broader context of the systems that we're trying to interrogate and understand and really advance our ability to intervene within advanced malignancies and ideally other diseases as well. And so as we start to evaluate the opportunity, it's really important to start to think about how we can move from a symptomatic definition of disease to a molecular definition of disease. Today and previously, we've always used symptoms to define how we start to characterize disease. That's something that has been developed because of inherent limitations in technology that exists. Whereas today, with next generation sequencing, we're able to start to move beyond that. And so we're finally able to start to look at the molecular nature of cells, what perturbations are driving disease, and define that in a way that allows a finer resolution for each underlying malignancy type. So as we start to think about this, we can approach it from a mathematical perspective. And this is really a highly complex system that is adapting to evolutionary pressure applied through various therapeutic interventions. And so what we really want to start to do is understand where exactly are the tipping points? How can we push one patient's response in one particular direction compared to another? And that's what precision medicine affords us. That's what we can start to do with this information that we're able to generate en masse across a multitude of different patients. And so as we start to think about the complexity of the data, we also want to be keenly aware of first principles. And so, of course, when we're talking about molecular biology, we've got to go through that central dogma. So we've got about 20,000 genes that we can measure, and those turn into hundreds of thousands of transcripts, of which maybe 60,000 or so are most useful. Those are turned into millions of different proteins and protein complexes. We try to contain them and estimate the number, but really we don't have the technology that's capable of addressing the sheer complexity that exists within our system. And so we're using surrogate data points. And so, inevitably we start to rely on DNA. It's the easiest thing to measure, but it has its own limitations. And so we go to the RNA, and we're capable of measuring that fairly well, but it also has its limitations. And so as we start to understand the nature of the molecular information that we're generating, it's also important to be aware of the limitations of those data sources. That at the end of the day, it's not the DNA that's driving everything, it's really the formation of these protein complexes, but we have to use the surrogate information that's available to us. And a really good example of how DNA and mutations don't tell the whole story is actually the domesticated swine. And so in captivity, they are stuck in a permanently juvenile state. That is due to diet, it is due to a low stress environment. But when they escape, it can take as little as 3 months for them to go through a pretty significant phenotypic transformation. They grow these large tusks, they get all hairy. There's no change at the DNA level. This is only a change within the phenotypic presentation of the animal due to changes in testosterone, due to changes in the hormonal system. And so as we start to think about what information can we glean from DNA, what information can we glean from RNA, and how do we get to where we can actually measure everything in the protein, it's important to be aware of the limitations of that information. Now, that being said, we're on the cusp of a revolution in science, in molecular science, because of the invention of next generation sequencing. And if you think about the context of that, it's actually very akin to the invention of a microscope. And so back in the day, before we had microscopes, we had no idea about germs and bacteria. But once we could start to see them, then all of a sudden we could start to understand them. And arguably, the invention of penicillin and of antibiotics has led to more improvement in human health than anything else ever. And so now with next generation sequencing, we're in a similar situation. We have the opportunity to make measurements and see things that we could never know before. And so it's up to us to utilize that information to maximize our ability to improve the human condition. And so as we start to think about that technological revolution that's really underway, it comes down to some very simple numbers, large numbers, but simple numbers. So if we normalize everything to the data required to look at 100,000 patients at 500x depth of coverage across their exome and their transcriptome, then we can start to look at the relative cost and improvements in technology. And so if we tried to measure those 100,000 patients at 500x depth of coverage back in 2001, that would have cost over $20 trillion. If we tried to do it in 2011, it would have cost over $3 billion. Today, when we do it, it's costing more like $150 million, which is still a lot of money, but relative to the amount of data that we're getting out is reasonable to start to pursue. And so it's incumbent upon us to start to gather as much of this information as possible, because it's only by looking at everything that we're going to be able to start to truly understand how best to intervene on a patient's behalf to improve their particular outcome. And so, right now we have a habit of defining genes as being clinically actionable or not, which is really more a function of the available therapies and not necessarily the genes themselves. And so as we start to think about how many genes are there that are cancer genes, how many genes that matter, the answer, maybe not surprisingly, is basically all of them. Every gene is a cancer gene. And so there's been some nice work evaluating this lately. And so if we look at it, of the 17,000 genes that have been published in PubMed, 87% of them have at least one mention of cancer. And so at the end of the day, we know that every single gene can be involved in cancer. It doesn't mean it's the driver, but it means that it can be a passenger. And that by understanding the perturbations within the molecular system, we're going to increase our understanding of how best to identify and intervene on patients' behalf. And so, we've focused all our efforts on a relatively small number of genes because they've given us the biggest impact, but also because of the technological limitations. It wasn't really feasible to run whole exome and whole transcriptome on every single cancer patient, but it is now. The technology is available to us, and we can do this in routine clinical testing to be able to gather this information and really start to expand our understanding of patients' disease and how best to make it better for them, to find new opportunities to treat them, to find new drug targets and develop new improved therapies. And so at the end of the day, that diagnosis is of critical importance. It's the first step in this process and one that we can improve upon. Because at the end of the day, the very first step in treating a disease is diagnosing it. And so as we start to look at the nature of the molecular aberrations behind cancer types, we can see these patterns in the underlying mutational spectra. We can see patterns within the expression profile, within the copy number profile, that enable us to identify these particular diseases, and is eventually going to lead to new definitions of various cancer subtypes that are driven by the particular alteration that is the foundational element in the cancer. And so we can look at the work that's already been done, looking at tissue-specific molecular alterations, and how that can help define and differentiate disease types. That's especially important when we don't know the primary. About 5 to 7% of cancer patients, metastatic cancer patients, do not know what type of cancer they have. And so the way that we treat a lung cancer is very, very different than the way we treat a colorectal cancer patient or a pancreatic cancer patient. And so knowing the nature of that disease is of critical importance. And something that the molecular information that we're now able to generate can provide a significant role in improving and defining. And so as we start to think about this, and as we start to put into context the ability to measure all of these different genes, both at the DNA and the RNA level, it really creates a new opportunity. And so I have access to this data set from Caris of over 145,000 whole transcriptomes. And with this, we can start to see patterns in the biology of cancer that allow us to start to refine and define disease in a new way. And so when we're dealing with these incredibly large data sets, it's all about de-dimensionalization, reduction in the dimensionality of the data. We can't truly handle millions and millions of data points per patient because the false discovery risk is incredibly high. And so we can use our knowledge of biology, of pathways, of genes that are associated with one another to reduce that underlying question and come up with features that allow us to start to define disease in new ways. And so we did a 28,000 de-dimensionalization of the data, and then did non-supervised clustering. And that allows us to see these very distinct and related groups of patients. Patients whose disease is very similar at the molecular level, but what does that mean? How can we start to make sense of this? And so we can start turning on labels for the type of cancer that is there. And so if we look at colon cancer, that generally clusters in one particular area, but there are outliers. There are different types of colorectal cancer that we all lump together today, but maybe we shouldn't. If we start to look at lung cancer, at ovarian cancer, at glioblastoma, very, very distinct biological cluster, something that is very different from everything else that we know about cancer. All of these start to emerge as very distinct opportunities to enhance our understanding of disease. And at the end of the day, every disease is going to be that. And this is just a two-dimensional representation of a 28,000 dimensional space, but it provides context in terms of how we can start to use this molecular information to better define and understand disease. So you may be asking yourself, what does this have to do with liquid biopsy? Why am I talking about expression of tissue? It's because this is the foundational of truth. So the opportunity afforded with liquid biopsy is to have an insight into what's happening in the tissue through this non-invasive procedure. And so we want to understand how much of this information from the tissue are we able to find in the blood. And that comes down to the underlying biological substrates that are available to us. And so we can start to look at circulating tumor DNA, we can look at circulating tumor RNA, we can look at exosomally derived or extracellular vesicle derived RNA, we can look at circulating tumor cells, we can look at tumor-educated platelets. For the most part today, liquid biopsies are focused on circulating tumor DNA. That's a missed opportunity. The RNA component is very, very full of information. And so by adding in RNA, we can do a lot more. Circulating tumor cells have been studied for a long time. They're more rare. It's a more mature but difficult source of information. And the tumor-educated platelets are still a little bit early, I think. So my main focus is going to be on these three areas in terms of biological sources of information. And so as we're measuring these, the context of what we're doing is of critical importance. Because if we just look what's in the plasma, we're missing something. What we're missing is what's in the buffy coat, that genomic component for what's there. And that has a very important role to play that I'll come to in a little bit. But our ability to measure things should be the rate limiting factor, and it's not. And so running smaller gene panels is squandering an opportunity to maximize our understanding on a per patient basis. And so what we really want to do is try to find solutions to inherent biological limitations. There's a relatively small percentage of patients that have a lot of circulating cell-free DNA. As the stage of cancer advances, the number gets larger, but we need to be aware of these limitations and try to maximize our ability to do the right thing by patients. We want to miss as little as we can. We don't want to call things positive that shouldn't, and we might as well take the opportunity to get that hereditary piece of information. And so there are a number of technical challenges, both biological and from the technological perspective, that are limiting our ability to maximize our information. And I'm going to go through a fair number of those. And so addressing things like complex signatures, LOH and TMB, require a deeper understanding of what's going on. And so we need to start to look at how many unique biological molecules can we actually measure out of the blood? Because that's a driver for the depth, and the depth is the fundamental attribute that defines the underlying limit of detection for these rare biological events. And so if we consider this, and it's colloquially called the shedding problem, we know that it varies by tumor type. We know that it varies by stage of disease. And so the more aggressive the tumor type is, the more well vascularized the tumor type is. In general, the more cell-free DNA there is, circulating tumor DNA. And the later the stage, the more there is. And so this provides a framework by which we can start to evaluate the opportunity. Because if we're only able to find cell-free DNA or circulating tumor DNA in 40% of stage 1 cancer patients, Well, that means that at best for early detection, we're going to maximize our sensitivity at 40% if we're only looking at circulating tumor DNA. So it's of critical importance that we be aware of these underlying limitations and put them into context. Another really important component is to look for false positives. So the underlying number of mutations and the mutations observed in plasma are not all tumor-derived. There's a very significant contribution from clonal hematopoiesis of indeterminate potential, CHIP mutations for short, and those are important to start subtracting out. We don't want to start to act on these. They're very common, as it turns out. It's a function of age of the patient, and so the older we get, the more of these accumulate, and a lot of the genes that are mutated are also mutated in cancer. And so we want to be cognizant of the fact that when we see these somatic events, and they are somatic events, they're just not tumor-derived. They're coming from an alternative source. And the last thing we want to do is treat a patient based upon a CHIP mutation where we're not attacking the tumor when we think we are. And this is a very real thing. And so about 10% of men with advanced prostate cancer have a CHIP mutation, and often in ATM. And that could lead them to being treated with a PARP inhibitor when they should not be. And so it's really important to start to understand these. And we can do much better if we sequence both the plasma fraction and the white blood fraction, because we can start to understand what is CHIP and what is not CHIP. Not always. It's going to be difficult, especially in those really low variant frequency events when the two populations converge. But the more insight we can have, the better. And this is part of the learning that is ahead of us. We need to be able to start to understand, what is actionable, what is not actionable, what is an accumulation of white blood cells as opposed to what is coming from the tumor. And so that's the opportunity that is afforded by the advancements in the technology, where we can actually start to measure more than just what's in the plasma. Another component, of course, are the germline alterations. If we're going in and we're measuring what's in that buffy coat anyway, then we're going to be picking up those 50% alterations that are almost certainly inherited. And so we shouldn't just turn a blind eye to that. We need to evaluate this. We need to be mindful of the impact that that can have on the patient's family and their progeny. And so including an assessment of germline is part of that workup, because as we have begun to understand, the number of patients that have germline pathogenic mutations is quite significant. It's somewhere in that 8 to 15%. And the more data we collect, the more we can start to see it. The more advanced disease, the more often we're finding them. And so, these last three studies are probably the best studies, but they're targeting different patient populations. So TCGA has a lot more earlier stage disease than the studies coming out of Indiana and Michigan. And so when we're talking about later stage disease, then, it's probably up here in that 12 to 15%. Earlier stage disease, it's going to be a little bit less. And so again, putting it into context is important. And then the final component, arguably the most important component, are the false negatives. So what do you do when you know that a tumor is harboring a mutation, but you cannot find it in the blood? Is that because of a technological limitation? Is it because of a biological limitation? Or is it due to the underlying evolution of the tumor in response to therapy? We have to consider all the different reasons why that can be happening, because in general, when you use tissue as the gold standard, blood, you're only getting somewhere between 55 and 65% concordance. And so there's a significant number of mutations that do not show up in the blood and are known to be in the tumor. It's a difficult number to get to, though, because most of the patients involved in these studies were receiving treatment or had received treatment. So these are not necessarily time-contiguous sample collections, which would be important to do the best possible job of assessing that. And so at the end of the day, though, this limitation of sensitivity is a function of the number of biological molecules that can be measured. And so what we want to do is maximize the number of biological molecules that we're capable of measuring. And what that comes down to is looking for as many sources of information as we can. That's the advantage of going to cell-free DNA and cell-free RNA. So we can think about things not in terms of the underlying nature of the molecule, but circulating nucleic acids in general. And so the CNA opportunity is significant, because if we think about it, in 1 nanogram of DNA, you've got about 300 copies of each gene. In 1 nanogram of mRNA, you've got about 10,000 copies of each gene. So by adding in that secondary source of biological information in terms of RNA, we're expanding the number of unique molecules that are going into the assays. And that is the fundamental driver of assay performance. So as much as we want to sequence, that is not the rate limitation. What's rate limiting are the number of molecules we can put into the assay. We're doing PCR as part of next generation sequencing. And so you can sequence 30,000x depth of coverage or 50,000x depth of coverage if you want, but that's not adding additional information, because at the end of the day, we're not adding in hundreds of nanograms of underlying material. We're lucky to get 20, 25 nanograms of material. And so it's that biological input that is rate limiting. And it's really important to put that into context, because if somebody is reporting very, very high depths of coverage, they're certainly counting PCR duplicates. And that's not new information. That is just a rehashing of information that we already have. So it's the unique biological measurements that matter the most. And we can look at that relationship between nanograms and depth and loss and limit of detection. And so we can think about this in terms of those areas of the genome that are relatively easy to measure and hybridize to and pull down, as opposed to those that are more difficult. And so the lower the depth, the more difficult it is in cases where you have uniformity, but it creates this gradation. And so if we want to hit, we can reverse the process. Let's say we want 0.1% variant frequency in terms of limit of detection, and we want 5 observations of that mutation. Well, then we need a depth of 5,000x. To get to a depth of 5,000x, if we've got good quality region, then we need over 60 nanograms of input. If it's a really tough region to sequence, we may never get there. And so looking at the nature of what we're observing, looking at the potential for increased or decreased depth based upon the inherent sequence is essential to put this type of data into context. And so this is a fundamental limitation, not of liquid biopsy per se, but of the biology of what's measurable in the blood. And so if we pull 2 tubes, 2 10-mil tubes from a patient, we can get 8 mils of plasma. In 8 mils of plasma, you're still going to be limited. You're still going to be lucky to get 30, 40 nanograms of cell-free material out. And that's a rare patient. In many cases, it's going to be much, much smaller in terms of the amount of material that we have. And so it becomes absolutely essential for us to understand how much material went into this assay, because that's going to be the driver of how sensitive we can be in finding these mutations and how much we can trust them if we see them lower than that. There's a lot of noise in these systems. There's a lot of sequencing error that can be introduced, and we don't want to mistake sequencing error for something that is biologically real. That's a different type of false positive that is equally or more dangerous for patients. And so as we start to think about this opportunity, we can start to define our ability to see these things and relate it back to the tumor in terms of that non-sheddar rate, to say, okay, if we have less than 5 nanograms, then we're not going to run it. If we have less than 10 nanograms, we're not going to run it. And what does that do in terms of the percentage of non-sheddar? The larger you make that threshold, the higher your non-sheddar rate. If we accept all comers, then we can sit in that 40% concordance, some coming from the DNA, some coming from the RNA. What we know is that the combination of the two is better. As we get more material, as we force there to be more material, then things improve, but at the expense of not being able to provide information for patients. And so there's this natural trade-off in terms of how many people can we help and how well can we help them. And we don't necessarily need to set strict thresholds, but we do need to be cognizant of the limitations, and it should be well reported for this particular input. What is the limit of detection for this patient? Because that's easily determined and something that patients deserve to know and doctors deserve to know. And so as we go from kind of down in the weeds of the technical attributes of liquid biopsy and think about what is the opportunity that is in front of us with this technology, it's really well beyond oncology. And so at the end of the day, every single disease out there is cells going wrong. And if the cells are going wrong, that means that there's something within the molecular system that's going wrong. And the more data we collect, the better we're going to understand these. And we have a very unique opportunity in oncology because we actually have access to the raw cells, to the diseased cells. And so we know what ground truth is. And we can start to compare what we observe in the blood back to that ground truth. And that enables us to start to advance these assays and these techniques. And so utilization of this technology and the learnings in oncology should be applied elsewhere. Because with Alzheimer's disease, you can't go in there and biopsy the brain of a patient. You don't know what it is that we're looking for. And so as we can start to understand the relationship between aberrant molecular signaling in the tissue and those features that we're able to see in the blood in oncology, we can use those learnings and start to apply them elsewhere. And so at the end of the day, this technology very much is the new microscope. It is a new molecular measurement system that properly utilized is going to redefine medicine as we know it. And so it's incumbent upon us to make sure that we're well defined, that we are properly defining the limitations of these technologies as well as the opportunities. Because this is going to be the future of all medicine. You can see that day when every single patient is getting a blood draw and we're sequencing everything that's in there and able to define you're at risk of developing lupus, or you're at the risk of developing rheumatoid arthritis, or you're in the early stages of dementia, or you have pancreatic cancer. And so it's really incumbent upon us as the scientific community to be very thorough in the development of these technologies and make sure that we're preparing the world for the opportunity in front of us, because what we're experiencing really is a molecular revolution in medicine, and the opportunity to improve the human condition is greater than anything else in the history of science. And so with that, I would like to thank you for your attention and hope that you're enjoying the conference. Thank you very much.